Okay, here is a task that I always feel excited when I ask my student to do it every year. So as you know, we talk about ideal gas law, and in case you don't remember the formula, it is PV equals to nRT. And once again, it was actually three gas law that got combined into this ideal gas law. So I would want you to illustrate the relationship between two of the factors in the ideal gas law on the graph. So let's say for the first one, it will be pressure and volume. And the way that you can do it is by looking at the ideal gas law, and the other things would be remain constant. As I said over here, the control variable would be the other one, other than the two that you're doing. So for example, if it is pressure and volume, then that means the nRT will be a constant. So this should give you some insights on how the relationship it will be. So do it for all three graphs, and for each of them you need to draw three lines for a different values of the remaining control variable. So for example, if it is pressure against volume again, you should have three lines on the graph that represent a high temperature, a medium, intermediate temperature, or a low temperature as well. So there should be three lines, and you should label them, and it will be quite challenging to do. The hints I can give you is for the axis, you should think about whether or not there is negative or not. So for example, pressure cannot be negative and volume cannot be negative, and therefore the axis you may want to set could be simply taking up these two like edge of the graph. But there are times where it may be negative, then you may want to leave some space over there. Okay. For temperature, I would like you to keep the unit as degrees Celsius on the graph. So instead of Kelvin. So this is something that let's keep it consistent for all of us, and then we can check the answers later on. So try it out, pause the video, and we'll check the answers later on.
A few moments later.
Okay, so for the first one, which is pressure and volume, is actually the hardest one, I would say. So let's say y-axis is P, x-axis is V. The first thing that you may want to do is refer to the ideal gas law again. So as you know, the only two changing are pressure and volume, and therefore this whole thing nRT will be a constant, and therefore you can derive the equation that is P1 V1 equals to P2 V2 from the ideal gas law itself. And that means the product of P and V value will be a constant throughout one single line. So let's say it is 10. How about that? So that means when P is, so you may get how about that? You can get a point that is 10.1 and 10.1 also here. You could also get a point that is 2.5 and 2.5 here. So you can imagine there could be a line that's something like a curve, which is very sensible. I didn't draw very well, but it should be a curve like this. And that could be one of the temperature. Let's say this is a low temperature. And then we can make the product bigger. Let's say it is 20. So we can make it as when it is 2, it is 10, and then same here, 2 and 10. When it is 5, then it will be 4, and when it's 5, it's 4. Okay, so then that could probably give you another line like that. And also you can see from the mathematical relationship that P and V, if that's the case, it would generate a curve to you, because you can see this is y x equals to a constant, so y equal to c over x. So it's an inverse function, which means it's like a curve like this. So the green one, let's call it the mid, or the medium maybe is better, temperature. And let's use maybe the blue one for the last one. and let's call it 40. How about that? So that means when it is 4, the other one is 10. When this is 10, it is 4. When it's 5, then it could be 8. So 8 is here, and then 8, 5 is here. So you can draw a curve like this, and then maybe extend it a bit more. Of course, you can find more points. But then here is just to illustrate you roughly how does the graph look like. So this could be the line that you're going to draw, and this is going to be the high temperature. Okay, so this is actually the hardest graph that you need to draw among these three. For the next one is about volume and temperature. So first of all, once again, you may want to deduce from the ideal gas law. Of course, if you do it more often, then you know you can do it more quickly. So V and T are changing. So V over T to move it on one side, leaving NR and P as a constant, and therefore V1, you may say a constant here, and then V1 T1 equals to V2 T2. And since I said temperature, we would like to use degrees Celsius scale, and therefore you could foresee that there could be negative value. So maybe I just pick the middle, while volume of course cannot be negative. Oops, I didn't draw very well, so but that's okay, I think. If you got ruler, of course, I think you can draw better than me. And so in that case, you can actually see more easily that the ratio of T1 over T2, sorry, V1 over T1 is actually a constant, and it in fact in this graph is actually a slope. So that will mean depending on what pressure it is, then it will generate you a different slope. So you can imagine when P increase, then the slope, which means the whole thing, would decrease in that case, because it's under the fraction. So let's just draw one line. This time I think it's easier, we just draw a straight line directly. But if you draw this one as a straight line, then you are wrong, because what actually scientists find out is when you reach 0 degrees Celsius, you don't have zero volume. You only get that when you have the absolute value. So this point is negative 273 degrees Celsius, or I can put degrees Celsius here for simplicity. Only at that time, then the volume will become 0 in theory, of course. And so that could be one slope. And when I have the pressure increase, as I said, the slope would be less. So something like this maybe. It's still a straight line. I try to draw a straight line, but then the slope is less. So let's say this is medium, and the one before was low. Okay, maybe we should also put down the variable as well. So P, medium P, and lastly for the even higher pressure, the slope will be even less steep, right? More gentle in that case. Once again, that's because increasing P would lower the constant overall and lower the ratio overall. That means the slope. Okay, and lastly, we would have pressure against temperature. So again, pressure cannot be negative, but temperature for degrees Celsius could be negative, and so we would have the same axis. Sorry for my drawing, I can't really draw easily on my computer. Pressure this time. So the idea is very similar to what we did earlier. So let's just do it again. Ideal gas law, and then this time it's P changing with T, so P and T put together, while the other things move to one side, and that will make you a constant. And so we get P1 over T1 equals to P2 over T2 equals to a constant, which actually equals to the slope as well, because once again you can see y-axis is P, x-axis is T. So the way that we do is in fact exactly the same as part B. So we should have a point where it will hit x-intercept at negative 273 if this is degrees Celsius for a low volume, because it's the same this time that when volume increase, the slope would decrease. So that means the ratio would decrease, so the slope decrease. And so we could draw another one with a more gentle slope, and that is the medium, like slightly higher volume. And lastly, another one that is a high volume in that case. Alright, so this is the relationship between these three variables when one of them is fixed. Of course, here we also assume the n in the ideal gas law in any of the cases are always the same. N again represents the number of mole of the gas, and we are assuming there's no leakage and there's no air pump into the system, and therefore N remain constant. And therefore we only discuss right now the relationship between P, V, and T only. Of course, if you like to change the temperature scale into Kelvin, then you simply shift the graph on part B and C to the right, setting this point in the origin, and the whole thing would still be valid. And that is all for this interesting task. In your textbook, there are actually some examples on how the scientist or investigation can be done by studying each relationship between, say, P and V. You can have a setup like this. You can also find out the relationship between P and V. If you try to plot a graph, if you find out, hey, how come this graph is different from ours? And that is because the graph that we were plotting was P against V, and just for the sake of linearizing the graph, then the graph here chose to have P against 1 over V. And if you look at the relationship, of course, in that case, you can get a straight line. Okay, and you can read through all these things. And this is like one of the line that we draw. So technically, like I said, you can draw 3 more lines for different value of temperature. Here is an example. I think you can just read it by yourself, and the relationship is actually quite easy to find out. And you simply just using PV equals to PV, and you just substitute, and it's very easy. It's something that you could do it in IGCSE as well, so I'll skip that. I didn't put it in the question set, so take a look by yourself. For the volume temperature law, again, the setup could be like this, and so the volume may change according to the temperature. And for the graph, this is something similar to what we did, and this is exactly the same as what we did as well. Once again, the reason why scientists could predict absolute value is negative 273 was because they tried to do the experiment and they find out some data point right around here. Think about in the really long time ago, when scientists or the science itself was not very developed, having so much technology to help us to measure things are at the extreme, the data point that we may get could probably be mainly between 0 to 100. Just like what you'll be doing if you do something related to temperature in your IA, very likely you could only do in a range roughly like this, like unless you have something like liquid nitrogen or etc. Even that is not easy to measure because you need a very special thermometer to measure probably. And in that case, by regression, then scientists could use the mathematical model to predict this straight line. They all merge to one point, that is negative 273 degrees Celsius. And this is how scientists try to predict the existence of absolute zero. And I always find this very fascinating, that you could use data to predict in some extreme case, And eventually, in our current development, we could, of course, we could not actually reach this, but we could at least reach negative 272 point something. You can try to Google. And we cannot go even further, more negative, of course. And that actually so far verified the absolute zero temperature would really be negative 273. And the last law is the Charles law, which is V over T. And no, sorry, just now that one is V over T. And again, there's another example. Again, I don't feel it is necessary to go through it because it's just really simple. You just use the equation, substitute. Just be careful. The T is changed to Kelvin scale. So 22 should change to 295. You should know how to do it. And just find out the answer. For the last one, pressure temperature law is also the same. You can do experiments set up like this, and the graph looks something similar like what we did. So again, people by doing the data set around this region, and they can predict by extending the line. And that's something you may want to do as well when you're doing your IA. Try to extend the line and see whether when you extend the line, would it be sensible to extend, or whether or not it is not nonsense. And you can find out for different value of volume, you can have different slope in that case. Alright, so another example, which again I find very easy, so I skip that in the question booklet. So if you're okay with that, then we'll be doing 3 examples in your question set. So you may want to pause the video now, and we'll check the answers together.